benevolent
one.
elephants.
Check
11
one. Check
benevolent
two.
elephants.
Check one. I eat giant cookies. I eat giant cookies. I eat
Ooh.
giant cookies. Whew, that's good. All right,
And
start
that
recording.
concludes today's episode.
That's how you remember, by the
Welcome.
way, ladies and gentlemen, the large Galilean moons of Jupiter. I eat giant cookies. Io, Europa, Ganymede, Callisto. You're welcome.
Ooh, I
Yes.
like that.
Yeah.
Now do
Also,
all
I
the
like
moons of
cookies.
Saturn.
All right. No.
No.
Hyperion. That one. I like it.
Empyrean.
Hyperion's very
Welcome.
beautiful.
Welcome, guys, gals, and non-binary pals, to today's episode of Science Actually Presents the Nerd and the Scientist, where today we are joined, as always, by ourselves, your co-hosts.
It's a pleasure to still be here.
Yeah, it's a pleasure to still be had. Today's episode, we are continuing our countdown of the top 20 myths about space and busting them.
Bust them.
Busting
So
good.
we did the first 10 our previous episode. Space myth number 11. Mercury is the closest planet to the sun and therefore the hottest one.
That is what they would want you to believe. But that is not the case. Unfortunately, no. It is not Mercury, but actually Venus that is the hottest planet. And that is because even though Venus is not the closest planet, it has an atmosphere, and atmospheres trap heat. And so the greenhouse effect has trapped so much heat that the surface of Venus is significantly hotter than Mercury. Mercury does have a thin atmosphere, but not quite as insulating as Venus is.
Nope. Venus's atmosphere is something like 90 times denser than ours. It's insanity. It's hot.
Yeah.
The pressure is incredible. If you get to the bottom, you will be boiled and burnt alive before you even made it to the surface.
Yeah,
And
the
conversely,
probes,
on
right?
the side of Mercury that's facing away from the sun is so insanely freezing. It has glaciers of salt. It's just the side facing
Did
the
not
sun
know that.
obviously is incredibly hot, but the other side is just beyond cold.
Yeah, it's kind of it's kind of weird to think about, but you realize that the heat coming directly from the sun is only part of the story. It's about how you actually maintain and sustain that heat.
Right.
That's what does it. Yep. Next on the list, Saturn.
What about it?
Is it's very pretty and it's quite beautiful, and we like it. That's why we put a ring on it. However, Saturn is not actually the only ringed planet in the solar system.
It is not.
It is not. People used to think so. What can you tell me about this one, Benjamin?
Not only is Saturn not the only ringed planet in the solar system, all the gas giants are ringed planets. Jupiter has a faint ring that we've discovered is quite easy to see. The closer you get a probe you sent out there gets to Jupiter, the more easier it is to see Jupiter's very fine, very thin ring. Saturn has the most prominent ring system. It's incredibly broad and bright because it has just so many countless dust particles and snowballs orbiting that it reflects so much light from the sun. It makes it incredibly easy to see. But Uranus, if you keep going, has a ring, and Neptune has a ring. Uranus's ring, I think it's Uranus's ring, is so incredibly dark. It's like soot, but it's there, and it's easy to see if you pass Uranus and look back, and you have the sun and the glow of the sun behind Uranus. You can actually see it. And not just planets, but there are other ringed things in our solar system as well. There's an asteroid, Chariklo, which is somewhere between Saturn and Uranus's orbits. It has two rings. A 90-mile across asteroid, little minor planet, has its own little ring system. So rings are actually uh, not just something that Saturn does, but it happens a lot. They're everywhere.
Yeah. And it makes sense. It's often how things will form on different scales in the universe.
Mm-hmm.
Even planetary systems around stars will start by forming in a disk shape called a protoplanetary disk. What's interesting with Saturn recently is you might have heard about this in the press that people are talking about how Saturn's rings are about to disappear and people were losing
Right.
their minds.
How soon will
Basically,
that
just
happen?
because. God. No, there's just going to be this effect where I think over the next year there'll be a few months, like 3-4 months in a row, where Saturn's rings will not be perceptible. They will appear to disappear, just because of the angle Saturn is orbiting the Sun and that angle relative to Earth. But they're not going anywhere.
Yes. If you look
Oh
straight
man,
down on Saturn's rings, they are incredibly thick. If you look at them edge on, it's insanely thin compared to the rest of the thickness of it. And so if you look at it edge on from, what is it, 900 million miles away or something like this,
something like that.
it's so far away, it's too thin to see. Kind of like a previous myth that you can see the Great Wall of China from space. You're so far away from it, it becomes so thin you can't see it. Same thing with the rings of Saturn. If you look at them edge on,
There you go.
edge on,
There you go.
that's pretty cool.
There you go. This next myth.
This next myth, actually, I love because I did not know this.
I
I
didn't
honest,
either.
I actually thought it was. Well, let's get to it. When a spacecraft re-enters the Earth's atmosphere, it gets incredibly hot because it's from the friction of just screaming through our atmosphere. It turns out that's actually only a small part of what makes the fireball around a re-entering spacecraft. It's not just the friction of the atmosphere, which does happen, but uh, the spacecraft re-entering the atmosphere is shooting down so incredibly fast that the air that it's pushing through doesn't have time to get out of the way, which does contribute to the friction. But the air molecules are kind of pinned beneath the spacecraft that's coming in, and more and more and more and more molecules of our atmosphere just start stacking up upon each other underneath the spacecraft, which creates an insane amount of pressure, and that pressure produces intense heat. That's about it, really.
That's
It's
about it.
actually
Yeah.
it's pretty insane.
Yeah. Generally speaking, you'll see this strong kind of linear relationship between pressure and temperature all across science in all sorts of ways. But generally, pressure times volume is going to be proportional to the temperature. So if you imagine that you're basically decreasing the volume of a small, basically you're bunching up all of these air particles and gas particles into a smaller area, the pressure is going to continue to rise as a result to kind of balance the equation. But yeah, I didn't know this one either. It wasn't clear to me, but it was definitely a fun fact.
Do you see what he did there? You guys see what he did there? Kovi from Fun Facts Science just totally wove in the name of his little SciComm channel, Fun Facts Science, because he learned some fun facts about science. This is why you need to have a podcast, people. Kavi, Kavi, you are a star, and you twinkle like one. Hey,
Oh
Twinkle
god.
Toes. Why do stars twinkle?
Oh man, stars
Why do
don't
bad things
actually,
happen?
for the most part. Why do bad things happen to good stars? No,
Why
no
do
stars.
stars twinkle?
Stars only appear to twinkle. There are stars out there that do all sorts of interesting things that vary on different timescales, but that's not what we see when we see twinkling. When we see twinkling, what we're seeing actually are atmospheric effects, because the light coming from the stars is hitting different layers of the atmosphere. And as it hits those layers which are moving, the ray of light will kind of refract and change as it moves down towards us. And so the result of that kind of shift makes us see the light coming from kind of a moving direction. And that is what will make stars appear to twinkle. With planets, you'll be able to tell a planet from a star in the night sky because planets do not twinkle,
Nope.
because there are multiple points of light coming from a planet. Whereas a star, it's so far away that generally our eyes are only able to perceive that as a single kind of point source moving towards us.
Excellent. Also, there's, um, correct me if I'm wrong, but there's also more uh, debris between us and the stars than there is between us and the planets. Like clouds of gas and dust that could possibly be between us and the stars. Is that a possible contributor to a twinkle, or that's just something else entirely?
So, so I don't like what you're saying is physically correct and is a thing that happens, but I don't know if those effects are perceptible to the human eye. So
Mm,
what you're describing is something really interesting called scintillation,
that's right.
and we do see it with radio telescopes, right? We'll see, radio light coming from distant galaxies, um, and the light will scintillate. It will vary, up to a few percent, or even several percent, of its total brightness as it passes through intervening gas. Um, but I do not think that that effect happens on the scale of what we're talking about. The twinkling that we're talking about, what the human eye sees,
All
optical,
atmospheric.
yeah, that's atmospheric.
Mm, okay. One more, and before we do our little mid-show break from an incredibly cool sponsor coming up,
Sure.
comet tails. We love comets when they come into our night sky, and they're beautiful, beautiful things to watch. And a comet tail is an incredibly long structure that follows behind a comet, and it tells you exactly which way the comet is going. True or false?
So, well, yes, but actually no.
Mm.
Yeah. So this is something that it does tell you the way that it's going, but not in the way that you'd think. It kind of is something that I first learnt about. I think with what was it, the comet Neowise that had two
Mm-hmm.
tails, right?
Mm-hmm.
And the reason that you see these two tails is a comet is a collection of ice and dust, and when you have something icy that comes towards something hot like the sun, you have a process that basically causes that ice to turn into particulates and kind of steam off and push off this kind of like water gas into space. But when this happens, it's going to happen in the direction opposite to the direction of the radiation from the sun, right? So basically, whenever you have particles coming from the sun, those particles will whenever you have particles coming from the sun, those particles will be the thing that produces the tail of the comet. So it's not necessarily the direction it's moving in, but it's going to be opposite to the direction that the solar radiation is coming from.
Mm-hmm. Because it gets blasted straight back from the sun.
Yep.
If you drew a line from the sun to the comet, the tail would follow that line.
Yeah. And so it's a really cool effect that you see that as a comet kind of passes its closest approach to the sun, um, it will the tail direction will change.
I love it. Comets are
Fun
awesome.
fact. Yeah.
Fun fact, science. Nice callback again.
Another one. All right, time for today's commercial break.
I can't wait. Who is our lucky sponsor today?
I can't wait to find out because this is the first time that I'm reading this.
God.
Attention, cosmic explorers. Experience the cosmos like never before with a quantum celestial voyager, your personal ticket to the stars. This high-tech telescope is not just for experts, it's designed for everyone. Easy to use and educational, brings the wonders of the universe to your fingertips. But that's not all. The Quantum Celestial Voyager comes with an AR system for interactive stargazing. Imagine constellations and galaxies like never before. Order now and receive a free Galactic Explorer Kit, exclusive guides, posters, and more. Elevate your stargazing at quantumcelestialvoyager.com or call 1-800-SPACE-FUN. That's 1-800-SPACE-FUN. Blast off into a world of discovery today.
Okay. That sounded a little too good. It really did.
For those listening at home, that was ChatGPT's take on my question. Write me a radio commercial for a non-existing space-related product.
That sounds like it exists. That sounded way too good.
Oh man, I want to read the full version later because the original version that ChatGPT gave me was a little bit long, so I asked it to shorten it. I said, please shorten it, which is hilarious that we still choose to say please and thank you to ChatGPT. But the full version had like a whole interplay of like the narrator and then two customers, and there was a whole like a testimonial section. It was wild.
Wow. Way to go, ChatGPT.
I'll send it to you.
Please do.
Seriously.
Back to it.
Back to the show. Yes. What do we have next?
Next is a very hot topic. Meteorites. Meteorites are hot. And the myth is that if you see a meteorite on the ground, don't touch it. It's quite hot. But actually, it's not. By the time a meteor is hot, why is it's going through the process of streaking through the atmosphere and catching fire and doing a little bit of that re-entry stuff we talked about earlier. By the time it hits the ground, it's had a long fall through the atmosphere. It has slowed down. It has cooled down considerably. By the time it hits the ground, it is then a meteorite. And most of the heat by that point has dissipated. If you see a meteorite in the ground, of course, be cautious, but do not expect to burn your hand off. It probably won't happen.
Yeah, I guess it's kind of like aluminum foil or silver foil, as some people might call it. It retains as a thin layer of heat around something, but on the inside, the temperature will kind of be whatever it has been previously. So in this case, these are rocks that have been traveling through space for billions of years. They are not hot. They have no internal source of heat. So it's just that kind of outer wrapper, that outer layer that's causing, that is heated during this process. The rest of it is nice and cool.
That was a good one.
I like that. Yeah. The next one's controversial. I don't think you'll like it.
I have. The next one is that you can hear sound in space, but I believe this was already settled in 1979 in the first Alien movie, where they said, "In space, no one can hear you scream." So I think we're done with that one. No, it's settled. No one can hear you scream in space. Here it comes. Here it comes. Kovi hears people scream in space.
Yeah, I'm haunted by the screams of people in space. I think, generally speaking, the way that sound works is, it's a wave, it's a pressure wave that moves through material. So on Earth, we hear sound because something creates a pressure wave through the air. That pressure wave in the air travels and hits our eardrum, and then the eardrum vibrates, in line with that pressure wave. And that's it. That's how sound travels on Earth. In space, space is almost entirely empty. You're talking about a couple of atoms per cubic centimeter. So there's not a lot of stuff for a pressure wave to travel through, which is why generally people say, and it's pretty much correct, that in space you can't hear sound, you can't hear anything. I would say though that in the denser regions of space, in around the centers of galaxies or distant nebulae or clusters, there would be regions dense enough for a pressure wave to travel. And we can measure those pressure waves. And even if those frequencies that the waves are moving at are not necessarily ones that our ears could normally hear, we could, upscale them to frequencies that we could hear. So there are all sorts of cool sonification software tools out there that you could use for stuff like that. So that was my kind of little but drawn out caveat about the whole not being able to
That's
hear
good.
space.
That's very good. And also touched upon the next space myth, that space is a completely empty vacuum. It is not completely empty.
It is
In
not
the most
completely.
emptiest parts of space, you can find a few. What is it? Every cubic meter of space, you can find at least a few atoms tooling about.
Yeah, I think in the interstellar medium, it's like one atom per every cubic centimeter. So that's like one one hydrogen for every area that's the size of a dice. But that's not empty, and that's kind of on average. There are regions where there are more particles, as I said before, a bit denser. But yes, it's not completely empty, and it could never be completely empty because there are all of these wacky quantum mechanical things that prevent us from knowing something completely, having a completely zero energy or completely zero particle. Yeah, but it's pretty darn sparse, if you ask me.
Now, two more to go.
Two more to go.
We kind of touched upon this a little bit in the previous episode of Myths, but in space, there is, like, and you're far away in the middle of space, there is no gravity. There is some, yes. You're always feeling
Yeah.
the pull of something. The further away it is, the smaller its pull on you, but you're always feeling,
Mm-hmm.
even if it's imperceptible, there is still some gravity tugging you just a little bit.
Yeah, that's exactly right. So it's kind of like
No studying.
you don't need me for this show.
Bye.
Yeah. On in space, we have microgravity, especially on the International Space Station. It's called microgravity. So there's definitely the effect of weightlessness, but it's not like there's nothing. As you said, it's just a very weak force of gravity that's being counteracted by the movement of the International Space Station through space that causes this effect. But yeah, anywhere in space, if you choose a point in the middle of nowhere, there'll be distant objects that will be still very weakly pulling in that direction. Right. So, but again, as I said before, with the black hole myth, it's not an active pulling; it's kind of a passive pulling, like a falling. It's like space time will be slightly sloped downwards towards that object.
Right. And weightlessness and no gravity they're two separate things. The weightlessness we see on the space station is actually a prolonged falling.
Exactly.
The space station is always constantly in this perfectly maintained free fall around the Earth, and it's always adjusting itself. So should that stop adjusting itself, then the passengers aboard will definitely feel gravity
Yes, exactly.
in a bad
I
way.
think they would have a bad time. I think I'll hand pass this last one to you. Would we explode in space without a spacesuit?
No, we would not. Now, if you expose your body to the emptiness of space, will you explode? No, you're not going to have a good day. It's going to become very painful quite immediately, and you are going to die in about a minute. Uh, it's it's a very bad thing that happens. Now, um, the beautiful part about this misconception that without a spacesuit exposed to the vacuum of space, you'll explode or you'll instantly die or whatever. It's actually been proven that it's not true. If you suddenly get exposed to the freezing temperatures and the zero near vacuum of space, um, you can actually survive. There have been before astronauts get sent up into space and they wear their lovely spacesuits. Those spacesuits are tested in environments created here in a lab on Earth that very accurately simulates the conditions of space. And there have been instances a technician testing a spacesuit had a hole in it, and he went into a chamber that was incredibly cold, incredibly it was a vacuum, and he was exposed to the conditions of space, albeit right here on Earth, and he was released. They realized it's a problem, and 30 seconds later, he was brought out and survived completely. I mean, he got hurt, and it wasn't fun, obviously, but it was not good. Your blood will begin to you will swell up because you're mostly water, and water wants to freeze, and when things freeze, it wants to expand. So you're going to swell up. Your blood will they say your blood will boil, but I don't really think that's a good word for
You'll
it.
have a bad time. Let's
You'll have a very bad
Don't
time.
try this at home, kids.
And one little cinematic science fact that I like about this one little thing is for Stanley Kubrick's movie 2001, a main character had to leave his little pod and get back into a spaceship, and he did not have a helmet. And how could he have possibly done it? Stanley Kubrick actually brought on a bunch of engineers from NASA and said, "Is this possible? And if so, how would it be done?" And they very accurately depicted someone trying to jettison himself out of an airlock into another one, quickly shut the door, and fill the airlock with air. And he had to hold his breath, and he prepared himself. He actually did it. They actually did it quite accurately, scientifically speaking. Obviously, no one's actually done that yet, but it is possible to survive a very brief exposure to space.
There you go.
And the
Well,
banging in the background of Kavi's office means it's time to go.
yes, unfortunately, you have been listening to The Nerd and the Scientist, brought to you by Science Actually. I am one of your lovely co hosts, Kovi Rose. You can find me on at Fun Fact Science on all of the good procrastination platforms. Benjamin, where can the people find you?
I am a representative of Science Actually, the only representative of Science Actually, and you can find me primarily on Facebook, but I'm on all the other time wasters as well. Twitter/X, Instagram, Threads, Blue Sky, Mastodon, Hive, LinkedIn, TikTok, if you'd like it. Daily science facts, come and enjoy, and